All right. Good afternoon, everybody. Today, we're going to be wrapping up our electrostatics part. We have so far discussed what could cause electric fields and how charges would respond to that, but we have not really discussed the energetics. There will be a couple of points in this class that will seem a little tricky, so let me prepare you for it. So what we're going to be talking about is the electrostatic interaction between point-like charged objects. And then we're going to slowly generalize that, and we'll say, okay, well, what if we have a configuration where it's not just two charged objects placed some distance apart, but now it's a configuration of n charged objects that we place in proximity. And then you have to start being really careful about what you mean by the configuration, because you can assemble such a configuration by, let's say, we start with n charged particles, and then in that field that they generate, we place particle n plus 1. So when we place particle n plus 1 into that, we are placing it in an already existing electric field configuration. So what we will do after is we will try to say, okay, once you know what the final electric field is, what is the energy of all those charged particles placed in that same electric field? But that's going to feel very strange, because you have to always be careful to not include in that calculation the interaction of charged particles with themselves. And once we have made that generalization where we say, well, it's some kind of final charge density and some final electric potential, you always have to remember that we kind of sidestep the fact that there might be divergences there. But as long as you remember fundamentally what is at work is just potential energy of point-like objects working together, there should be no confusion. The second thing I want to talk about is where's the actual energy stored. So there are two ways to look at this. It's let's say we have a capacitor, and the capacitor is initially not charged, but then we're charging it, meaning at some point we're moving one charged object from one plate of the capacitor to another side. And in doing so, we establish an electric field, and that electric field develops between the two plates of the capacitor. Now, the next charge that you move from one side of the capacitor to the other, you move that against that electric field. And thereby you increase the energy. And in doing so, you also increase the electric field. And in the end, we get a completely self-consistent description where we have, for a certain charge configuration, there is also a certain electric field configuration. And once you know what the electric field is, you can take it one step further, and you can say, you know what, the only way to generate such an electric field is through a certain configuration of charged objects. So actually, in order to know how much energy is stored in this object, we don't even need to know where the charges are anymore, because that location is going to be completely uniquely specified by the fact that the electric field has a certain configuration, which means we can solve, if my camera doesn't go out of focus, which means that we can solve problems like this in a very elegant manner. We can just say, once we have arranged our charged objects in a certain manner, all we need to know is where's the electric field, how big is it, and we integrated the field squared, and then that gives you the energy stored in the capacitor. So in summary, once we have the electric field configuration, we know exactly how much energy is stored in the system, and we don't even need to know where the charged objects are anymore. And then we will take it one step further, and we'll say, you know what, the energy can be stored in the electric field even without any charged particles present, which is how, for instance, energy gets carried by electromagnetic waves. And we're going to have to suspend our disbelief when it comes to that for a little bit. But the reason I bring this up is we will run into a similar issue later on in the class when we talk about the Maxwell stress tensor. When we talk about the Maxwell stress tensor, we can do a similar thing. We can say how much force is how big is the force that is acting on charged objects or current carrying objects. And we're going to specify that uniquely in terms of only the electric and magnetic fields. And it's a beautiful thing that you can do that because you can take out the charge and the current configuration that are causing that electric field because they are already implied by the presence that you have a certain field. And if you have a certain field, that has to mean that there are certain charged objects and certain current carrying wires there. So we can do the entire problem knowing only where the electric and magnetic fields are. So we'll do a similar trick later, but I just want you to get ready for this because it always feels a little bit like you're sweeping something under the rug, but really there's no way that you can generate a certain electric field configuration without placing the charged objects in their desired location. So trust me, it all works out, but it's going to feel a little awkward. All right. All right. There's one more logistical issue. Not next week, but the week after, there is a conference in San Francisco that I'm going to be going to. It's the Biophysical Society. It's an annual meeting, and it's a great meeting. So, but that means that on that Tuesday, I will not be there. I plan to just do the same thing, just post a video, and hopefully you can watch it on your own time and study that that way. That's the last travel for me for this semester. So hopefully this will be the last virtual thing. Because also I forgot to reiterate, everybody knows next week we're all back in person. Okay. Potentials, work, and energy. So let's take a step back and say, well, if we have some kind of an electric field, so let's say we have some kind of a uniform electric field, field's pointing straight this way. This is our electric field, and we have some kind of a spot A and some kind of a spot B, and we place a charged particle somewhere here, and we move it from A to B. So there's a Q that we move, is moved from A to B. The question we can ask is how much work does the field do so the work done in such a path is usually just force times distance. So if this path has some kind of a length L, oops, it would just be the force times the distance. And if the force is of course given by Q times E, then it's just Q times E times L. If our path is not in the direction along these field lines, but for instance, somehow this particle ends up in position C, then the work done will be 0 because of course the electric field is not doing any work because the electric field is perpendicular to the path. So we can also in general then say, well, our work in general was going to be just some Q times E times the path. And of course, the path is going to be the difference in position. So this is final minus initial. If instead of this field being uniform, we can generalize this a little bit. So for instance, this is the electric field. We can generalize this. So for instance, there's this weird path from A to B. And at any point here, we can evaluate how much work is being done here. The dW work is being done here. Now, that work, would there be Q times E times dl vector, where dl vector is the is that infinitesimal path along infinitesimal path segment along this length of this path. So the total work, again, can now rewrite. We can just say, well, it's the integral of E dl vector. Okay. Now, my question to you is, write this as a function of potential. All right. Well, the trick is, of course, that you need to use the expression that, so write it again, so it's EDL. And of course, using the fact that E is minus the gradient of the potential, we get here a minus Q gradient of the potential dotted with dl integrated over the entire path. This is fine, this is correct, this is, strictly speaking, is answering the question, but it's a little one step short of having the final answer. So let's look very carefully at what this thing says actually. So this thing says that phi will change by some amount if you go in the x direction, x or the y or the z direction. Okay, then you dot that with the movement in the x, y, and z direction. So really what this dot product is evaluating to is just the infinitesimal potential change along that path. So we can actually write it as minus Q d phi. Because for every one of those paths, it will just change by a certain amount. And it will be minus Q phi final minus phi initial. Okay, so now let's talk about the sign a little bit. So we know that if the work done is positive, so the field is doing work, that means that the let's say the particle gains speed, kinetic energy, and that K increase must come from a potential energy U decrease, and therefore also a phi decrease. Okay, so according to that definition, this phi final needs to be lower than phi initial, right? So phi final needs to be lower than phi initial because the potential needs to go down. So that means that if that's lower, then the so delta work will still be positive, and we are all good. All right. And of course, we know that the potential versus potential energy so we have U is Q times phi. So you can also look at that work expression that we had before and then just pull those Q's into the U's, and you would find that the work difference is equal to minus the potential energy difference. So everything works out. So if we're going to our favorite model system, so let's say consider a single point-like charged object. Let's call it QA. So we have some kind of a QA, and it's generating some kind of an electric field. And again, for simplicity, I'm just drawing it as a positive electric field. And now I've got some kind of a particle B that I move from some point to some position here. And then I can ask myself, okay, how much energy is stored in this configuration? So we can ask ourselves how much energy is stored in this configuration. Well, it would be QB, oops, delta U would be QB times the potential difference. But of course, the final potential is the potential generated by particle A at the location of where particle B shows up. And if we started in infinity, then that means that we don't need to subtract the initial energy because the potential goes to 0, right? Because phi is Q over R. That's what we need to remember. So starting point at R infinity as 0, phi is equal to 0, which is why we choose that starting point. Doesn't always work. For instance, there are certain configurations, for instance, charged cylinders, where you actually get a divergence. If you go there, you need to pick a different reference point. But let's keep things simple. Okay, so what is that? Well, it's QA times the potential generated by charge A, which is, sorry, see, I'm trying to be careful and I'm already messing it up. So it's the potential is Q over the distance. And the distance is, of course, the distance between particles A and B. Okay, or just QB, QA over RAB. Now, note that this is symmetric, So if you replace your A with a B, you get the same answer. Now, hopefully that should be obvious to you, because of course, in this configuration, if instead of having particle B move into the field of particle A, we take the point of view that particle B generates an electric field and we move particle A into it, then that should still mean that the potential generated by that point B would be QB over the distance, and the distance is going to be the same for both. So this should work out okay. Okay, so this is your U of the configuration. Okay. More charges. Okay, so let's say we have a configuration A, B, C. And we can ask ourselves, how much energy is stored in this configuration? And I'm going to let you work on that a little bit. Well, let's be systematic about this. What we could do is we're going to say first, well, let's start with the configuration where we have just only only A and B together, and then we know that the energy is this over R A B. And then we can ask, okay, what happens to the energy if we add that third charge C to it? Well, we need to consider the interaction between B and C. That's going to cause the potential to change, as well as the interaction with A and C. So that means gotta take this, gotta do QC, QA over RCA plus QC, QB over RCB. And now, of course, if we add a fourth to it, we have to, let's say we're taking D, we have to then consider this one, and this one. So we can build our problem out of the pairwise interactions between the particles, because in the end, we will have just a sum over all the pairs, because we started with the pair AB that gave us one term, then we added number C to it that gave us two pairs, right? A, C and B, C, and then we add the third one, that's another three pairs. Okay, so we can write that. We can write that a little bit more, more abstract. We can say, well, it's the sum of I, where we go, let's say from A to B, so QI, oops, and the sum from C to C, that's the first one, where we have, this is J, this is QI, QJ, over, well, this is the distance, actually, J. Okay, so these are the pairs. So for instance, if we now, this is for only an A and a B and a C, if we now increase this, let's go. Oops, let me just go in one go. So it's, so it's 1 to n minus 1. And here the sum is from I plus 1 to n. This is QI, QJ over RI minus RJ. I'm being super verbose here. I hope that you appreciate that, because sometimes it's easy to lose track of where we are. Okay, now, what you can do is you can say, well, actually, this QI is, actually, let me not do that. So it's 1/2 the sum of I 1 through n, oops, and the sum of j 1 through n, but not I. So I'm doing everything, right? Qi, Qj, but I'm going to be double counting my pairs, and I'm excluding the self interactions. So this is double counting pairs and not counting self interactions. Okay, so now I can factor out 1/2 1 through n. This is Qi. I'm going to factor out my I. And then j 1 through n, not I. This is Qj. This is Ri, and this Rj. Okay, this expression is, oops. This is the potential at location of Qi. So we can write this as 1/2 the sum 1 through n Qi, and then the phi at the location of the ith charge. So this looks a little bit different. Oops, looks a little bit different because of the fact that we have now a single sum here. Actually, let me move this around a little bit. Qi. So what does this mean? So once all other charges have been placed and we know the potential, just place Qi in it. And we can generalize this for continuous charge distributions. That becomes 1/2 rho, which is a function of position, times phi, which is also a function of position, integrated over entire space. And in shorthand, this is how sometimes you find it in the book: 1/2 rho phi. And this is the point where I need to talk to you a little bit about how weird it is that we can write it like this, because we were being very careful to avoid the self interactions. So if you strictly do this for, let's say, a set of point-like configurations, you're going to get weird divergences. So we usually don't use this expression for point-like objects for that reason. Okay, so this is something that you would use for continuous charge distribution is not for a configuration of, let's say, 3 or 4 charged objects. Then you would use the sum explicitly. Okay, so now let's talk about where is the energy stored? This is a bit of a philosophical question, but let me try to explain what my thinking is. So let's say, so take a capacitor. And it's charged. So that means, for instance, this is top plate, and this is the bottom plate. Then let's say it's let's say this one's positively charged, this one's negatively charged. What that means is that there's positive charges here everywhere. There's negative charges here everywhere too. And now we can say where is the energy stored? Well, there are two things that happen when we are charging it. We are moving charged objects onto those conductors, and we're also generating an electric field. And those two go hand in hand. And later on, you will see that actually electric fields can carry energy, which is how we get the displacement current, for instance. So it's really not that strange to think that actually the energy is actually it's stored in the field. In this case, the E field. Furthermore, once we know what the electric field configuration is, once we know what the E field configuration is, the location of the rows is implied, because we know that 4 pi rho, right? So the electric field will tell you where the row is. So can we therefore write U as a function, of E only? And the answer is, of course, yes, you can. So let's start with this first expression. So we know that U for continuous charge distributions, which is, for instance, the case in this case. So we have our rho, and we have our phi, and we integrate that over the entire volume. We would like to say, can we remove this explicit mention of a rho? Well, yes, we can. We can use the Poisson equation. Which says that the Laplacian of phi is minus 4 pi rho. Okay, so that means that we can write this as 1/2 integral. Now here we need to write the Laplacian of phi multiplied by phi, and we're integrating all of that, and we are carrying minus 1/4, of course, to keep everything the same. Now, let's look very carefully at this expression. So if you use the product rule on this expression, then what you get is the gradient first acting on the phi, and then the gradient acting on the gradient of phi. So what you get is you get the gradient acting, the gradient acting on phi dotted with the gradient acting on phi plus phi gradient squared phi, right? Because you first let the gradient act on this, which gives you this term. And afterwards you let it act on this, and then it gives you this term. So therefore, we can write phi, Laplacian phi, as the gradient of, as the divergence of this funky term minus the gradient of phi squared. All right, well, what's the point? Hopefully you can start seeing things coming. See, this is actually E. So we'd be getting closer home. The only thing we need to do is, what are we going to do with this? Okay, so let's get back to our expression. So now we have u minus 1/8 pi. And now we're going to get two integrals. One is the volume integral over this divergence of this funky field. So integrated over the volume. And now mind the plus. Okay, we have a volume integral squared dx. Okay, well, let's see if we can do something about this. This first term, we can use our famous identity that I keep forgetting the name of. So we can write this as the integral over the edge of phi, gradient of phi dotted with a surface. So we can write this. Oops. It's very hard to write straight lines. Okay, we can write this as this. Okay, and you fix this. This is over V. Now, if we let V go to infinity, we know that phi goes like 1/r usually. And the gradient of phi will go like 1/r squared. And we know that the surface area will go like r squared. So that means this is 1/r. This is 1/r squared. And this goes like r squared. So this whole thing goes to 0. So this part goes to 0 if we make sure we integrate over sufficiently large oops, sufficiently large volume. All right, so what we mean by that, we do this over sufficiently large volume in the sense that we want to make sure that we capture that part where the potential starts to go to zero, and then we say that's where we put the cutoff, or we just integrate over the entire universe. Okay. So therefore, we have u 1/8 pi, the volume integral, e squared d 3x. Okay. And again, I want you to look at this expression and realize it's a little weird that we can do this, that the presence of rho doesn't even show up. And again, the E configuration implies rho, but it's not as simple as that, because also later we will see that this is the energy actually carried by electromagnetic waves. And of course, there we usually can talk about the energy carried by an electromagnetic wave without considering the fact that they were generated at some point. We just say, hey, there's some energy and it's flowing from one place to another. And this is the energy density, and it's given by the electric field squared.